No, thank you so much for the invitation. I'm very happy to be back, and as I was thinking a joke, the last time I was in this room was when I graduated from my bachelor's. So the ceremonies, at least back then, were here. So it's really nice to be back here. So yeah, as I said, this is going to be 3 lectures on this topic of quantum aspects of near-extremal black holes. I'm pretty sure I always have like way too much material that I'm going to cover. I'm pretty sure I'm not going to be able to cover everything. But what I'm going to do, what I'm going to give the organizers, and I'm not going to write it here right now during the lectures, I'll give a list of references because there's many things that I'm not going to say. There's many topics that I'm not going to cover. So because nowadays it's quite a vast subject. But please, in any case, do interrupt me, ask me questions. You can ask me questions either in English or in Spanish also. So just feel free to ask, okay? Because I'll definitely be asking you guys questions. And so my first question in that regard is, because I basically know very few of you, epsilon. So how many of you have done GR as a course? Okay. So we all feel pretty comfortable with what a black hole is? Yes? If not, also please let me know. But yeah, so all of you, if I say something like Schwarzschild black hole, you're like, right, so Nostrum black hole? Maybe? Okay. If there's something that I'm saying that is too advanced or too out of reach, please let me know, okay? Because I know this stuff, and the point is that I want you guys to know this stuff. So things that are not clear should go ask. Yeah, you guys should just ask. Okay, so I wanted to start these lectures by basically first presenting the problem. Okay, I'll present to you an interesting aspect of black holes that maybe it's a very old problem, and maybe some of you already know about it. But the reason why it's the topic of this lecture is because in the last few years there was actually a non-trivial amount of progress in understanding this problem. Okay, and so that's what I want to share with you. But we'll start with what is the issue. Okay, and so to state the issue, we first have to talk about what are extremal black holes. So this is why I was asking if you guys already knew what black holes were. Because I'll take this as a granted. So we'll start from here, okay? So what is an extremal black hole? So let me, for concreteness, I'm not going to give a very formal definition, but I do want to set up the nomenclature so we're clear on what we have. Let's consider for simplicity 4D asymptotically flat solutions. Okay, so with 0 cosmological constant, just for simplicity. And in 4D asymptotically flat gravity, black holes are characterized by very few parameters generically. Okay, so in order for you to talk about black holes, you basically specify what the mass is, some electric charge, and perhaps some angular momentum that the solution has. Okay, and a property of these black holes is basically that for a given Q and J, there exists a minimal value of mass. Okay? M. And this is what we call an extremal black hole. So for example, let's just set up some values. So this might be something, I remember this was in my GR exam that Max taught me GR, my first course of GR, this was an exam question that I still remember. This black hole showed up in the exam. I believe I answered it correctly. So the mass is always bounded by this extremal value. And for instance, this extremal value is given by Q for j equal to 0. And for Q equal to 0. There's a general formula when you both have j and q that I'm not going to bother writing, but for simplicity, basically, these are basically the lowest, this M extremal that defines the extremal black hole. It basically has the simple expressions. So for fixed charge and angular momentum, this is the minimal value of the mass of the black hole. Okay? So if you saturate this bound, so it's extremal. And another case that we're going to be interested in is if you're near, slightly above, it's going to be called near-extremal. And of course, if it's below, maybe this is something that you would have seen in your GR courses. This is going to be a naked singularity. Okay, and usually what we like to believe in physics, there's not a proof, but these are basically physical situations. And one area that I'm not going to venture into, but basically trying to show that you can't achieve these physical configurations leads to a lot of theorems in GR, especially the cosmic censorship type theorems. Okay? But we're going to be basically considering what we call a black hole is solutions that have the mass greater or equal to this bound, and we're basically going to be focused on these two cases. Okay? So these lectures, just to set up the nomenclature, are going to be black holes that are very close to this saturation. Okay? And so you might ask, why? Why do we care? Why am I going to lecture about these type of black holes? What do we want to understand generic black holes? So what are the advantages? Why are we paying attention to these type of solutions? So there's at least, there's 3 reasons that I want to give about why we're going to be talking about this. Before I tell you about the quantum, let's just try to understand why the topic of these lectures are near-extremal black holes. So the first one is because as a theorist, what is the thing that we like the most as theorists? What's that? Symmetries. Yes, I'm obsessed with symmetries. I think symmetries are amazing, right? Symmetries give you power. And so the first reason is that there's an enhancement of symmetries. And this, we'll see it a little bit as we go through the examples, through the example. But basically the statement, just to give you a summary, is that there's a scale invariance in the near horizon region. And usually the way that we draw this, so let's say, since I'm considering this asymptotically flat black holes, so you would consider the black hole living on something that is like R31, let's say. Again, number of dimensions. This is also generalizes for cases that you have cosmological constant. But for simplicity, let's just keep it like this. What happens in an extremal situation is that there's a long throat that gets developed near the horizon. So we draw it like this. And so at some point here, there's the horizon of the black hole. And at this horizon, at this throat that I'm drawing here, is basically a geometry that is ADS2 times, well, depending on the situation, let me just write it M. In simple situations, for instance, in this one up here will be ADS2 times S2. But basically, this throat here, this region, has more symmetries than than a generic black hole solution. So here, in terms of symmetries, the scale invariance is basically a reflection that you have as scaling vectors, SO2R. One of these transformations is the scale invariance transformation that I'm talking about here. And this is an enhancement relative to just the U1 symmetry, or if you want, maybe let me not call it U1, just a translational symmetry of the generic black hole, where this R is basically just time translation. Okay, so you're going from something here that has 3 killing vectors. Oh, sorry, you start from something that just has 1 killing vector, let's say time translation, and in the near horizon of extremal black holes, you get 3 killing vectors. Okay, so you have more symmetries, and this symmetry is quite important because many dynamical aspects of extremal black holes are actually controlled by this SO2R. Okay, so many dynamical aspects okay, so this is one reason, first reason why we really like extremal black holes. When I pull it up there, yeah, you can still see it. Yes. Okay. Very good. Now, second reason. It's very much tied to the first one. And it's something that it's a little bit depicted in the picture. But the second reason why extremal black holes are nice types of black holes to study, it's for the reason that comes under the name of decoupling. Okay, so in general, like one of the things that that we would like to do, not always, but in a lot of situations, when we want to study black holes, and in particular, let's say, given the title of these lectures, quantum black holes, we want to be able to study the black hole as a quantum system by itself, in isolation, and not be distracted by the surrounding that it might be in. Okay? So I don't want to understand the quantum properties of flat space. I just want to understand the quantum properties of the black hole, not of the black hole necessarily in flat space. You might be interested in doing that, but for some questions, just given that there's a lot of things about the quantum properties of black holes that we don't understand, we want to be able to isolate and just capture the physics of the black hole. Okay, so from the surroundings, and basically this throat that I'm drawing there is a reflection that you can decouple. Basically, you can detach the black hole from its surroundings. So this long ADS2 throat is a manifestation that we can remove flat space from the black hole. Okay? So in many situations, then it facilitates interpretations, it facilitates computations. Just knowing that basically, so the picture might be misleading. This throat is infinitely long, and so basically what you can do is you can, and I'll do it as we go through the examples, you can just detach basically the top from the bottom and then just understand the geometry at the bottom. Okay? Yes?
The large throat is a feature that is only for this kind of platforms? Or
It's very much attached to extremality. I don't know any other situation where you can do this if it's not extreme. Yeah. Usually, yeah, for sure, like in the simple situations, I know for sure that you can't do this. So if you're not near the bound or at the bound, you definitely cannot do this. And the basic reason is because it takes you finite time to get to the horizon. Your proper time to reach the horizon of a black hole is finite, and so it means that you can't, it's from that geometrical point of view, you can't see how you could like consistently cut things out. Now, yeah, so that's roughly the basic reason. But what happens when you do the computation of what is the proper distance that to get to the horizon of an extremal black hole, that proper distance is infinite. And that's a reflection of this very long ADS2 throat. The proper time is finite, which is a little bit confusing, but the proper distance is infinite. And that's why you develop this ADS2 as you go down. But you could have asked, why was the extremality special? Well, if it was going to happen, I guess it had to happen at an edge. That's the only thing that I can say. But yeah. Usually these things, if there are some people that try to prove them, like to show like generically why this happens. It's hard. There are certain proofs, but they're Lagrange independent. So it depends on the theory that you have. So there's works in 4 and 5 dimensions for certain types of Lagrangian theories that you can show that every time that you have extremality, you're going to have this ADS2 throat. But you could also have thought that you could have had some different type of geometry in the near horizon, and that is possible, and it depends a little bit in the matter content that you have. Okay, so what supports the black hole? Very good. Any other questions? No? Okay. Now, the third reason why it's advantageous to look at black holes, at these extremal black holes, is basically Hawking radiation. And in some sense, not Hawking radiation itself, but basically the absence of Hawking radiation. So this is also something that I don't want to deal with, okay? So black holes are basically thermodynamic objects. Is this something, again, maybe, are we familiar with the fact that black holes are thermodynamic objects? No? I'm getting less nods. Maybe I should have given a lecture on black hole thermodynamics. Yeah. Okay, getting kind of terrified. But basically, a nice property of extremal black holes is that they're extremal black holes have 0 Hawking temperature. Okay? Well, define again. I'm doing things, what I'm writing right now are kind of conceptual things. I'm not deriving them, but I am stating basically what are nice properties of these black holes. And then the third one is basically this fact that extremal black holes have 0 Hawking temperature. Okay? So, in some sense, this means that I don't have to worry, or usually the radiation process, it's almost negligible. Hence, okay? So I'm not going to be afraid that they're going to evaporate. Okay? So if it was a very hot black hole, you might worry, if I'm going to start doing quantum properties, you might worry that you should also take into account the fact that the black hole is radiating, that is Hawking radiating. Okay? But because I'm very, very low temperatures, or exactly 0 temperature, this is not going to be an issue. Okay? Now, those are 3 advantages. These are 3 properties that give you, as a theorist, if you wanted to understand quantum aspects of black holes, these are 3 knobs that are used, and we're going to be using them. Okay? Quite a bit. But now you can say, well, that's all good. But it also brings its headaches. Because another thing that you know as a theorist is that there's always conservation of difficulty. So when I have an opportunity, something else is going to come and bite me back. Okay? So what are 2 problems or issues with extremal black holes? And this is basically what starts the motivation for these lectures. So what are the computations that we're going to do and how we're going to understand them? Okay? So despite all these beautiful properties, the first property is its interpretation as a ground state. Okay? So the first property of so for these extremal black holes, we know that they have minimal mass. For fixed Q and J. Okay, that's nice. And they also have 0 Hawking temperature. This basically, these 2 things defines for me, like if I'm doing statistical mechanics or your thermodynamics, this is basically the properties of what you would have called the ground state of the system. Right? It's a configuration at 0 temperature and with minimal amount of mass. Okay, so in that sense, extremal black holes are understood schematically as the ground state of this gravitational system. Okay? However, there's a third property, and it's that if you look at the Wittgenstein-Hawking entropy, which tells me that the entropy of the black hole should be its area, and this is the first and last time that I'll write it with units. It would be the area of the horizon here. It will be the extremal area of this horizon divided by 4 times the Planck length squared times the Boltzmann constant. And this expression for the extremal black hole, just so you can see it, with all of its units in glory, and even the speed of light, I'll dare to write it down. this thing is not zero, this entropy. And it's actually huge. So if you grab something like M87, which black hole is M87?
First of the four.
What's that?
The black hole of the first four.
The first.
The first. What other things are?
Photo. Sorry. Yes. Yes. From the Event Horizon Telescope.
Yeah.
Yes. So if you plug in the numbers for M87, this black hole entropy divided by the Boltzmann constant is of the order of 10 to the 70. Okay? This is huge. Why is this a problem?
Because of the first law.
What's that?
Because of the first law of thermodynamics?
No, not the first law.
There is a generation in the ground state.
There's a large ground state degeneracy. So it will be more like the third law, depending on how you state the third law. But basically, there's a huge ground state degeneracy. And what did they tell you in StatMech or in thermodynamics as the temperature goes to zero and you hit the ground state? What is the entropy? Zero usually, right? Because the ground state, in most of the systems that you're familiar with, the ground state is unique, right? Sometimes there can be a residual symmetry, so you get a little bit of ground state degeneracy. Or sometimes you can have something like supersymmetry that can explain why you have so much ground state degeneracy, why you have so much degenerate states. But in some sense, in generic situations, and here I haven't told you anything specific about this black hole. I'm not embedding it in something that has, like, this is for any given extremal black hole that you will have. Generically, their areas are not zero, and generically, you have this huge amount of entropy. And it's not obvious what would be statistical systems that it will have this huge amount of degeneracy. This is very confusing, okay? There was a time where people actually were trying to argue why this answer was zero. And then with supersymmetric black holes and in the context of string theory, it was possible to account for this thanks to the help of supersymmetry. Then people became more accustomed to it. They're like, oh, maybe it's not that weird. But still, this is not okay. Like 10 to the 70, like ground states, it's a lot. Okay? Well, this is the logarithm of the number of ground states. It's a lot. It's a lot of entropy. So what's going on here? How do you explain this? Not clear. Now, the second puzzle, so this is one of the problematic aspects of extremal black holes. So now if I wanted to understand quantum properties, I need to understand what that number means. Then the second problem, it actually ties a bit to this Hawking radiation problem. So the second issue is what happens if you go near extremality. So,
yes. Why is it a problem that the ground state entropy is huge if it's still a minimum? Because I would imagine that since you don't have access to what happens inside of a black hole.
It's just that because, like, give me examples of systems where the minimum is that highly degenerate. That's basically the puzzle. Everything that you've done in StatMech, usually, you would have gotten that the entropy is zero. That's the issue, is that it's not easy to fabricate or design systems that have this feature.
But it's still
In the absence of supersymmetry. So if you don't have supersymmetry, I don't know of any non-supersymmetric system that can have this huge amount of entropy. I don't know. Maybe it's because we're not creative enough, and so that's why people like, maybe this is not as fancy as the black hole information paradox problem, which is more problematic, but in general, like, even if so that's why I was trying to get rid of like the Hawking radiation and stuff, but like in general, like this is not, I wouldn't be able to tell you, like, what is the cup of tea that has this property, I don't know, like, so it's one of the issues. Again, if you don't have supersymmetry, this is a big issue. Okay. And it's basically that's the issue. I don't know systems whose ground states has this much the difference. Okay. Now the second issue. This one is a little bit more sophisticated. But what happens is the following. So this issue was noticed in the 90s, and it goes as follows. So let's look at the energy, or the semi-classical energy of the black hole near extremality. Okay, basically by energy here, I'll be using it a little bit interchangeably, energy and mass. So if I start from extremality, the energy is basically going to be this extremal mass. Okay, so this is I'm going to be doing an expansion in temperature. And so let me write it here. The energy is a function of the temperature of the black hole. So at 0 temperature, you have this mass. And then the first correction, which again, we're going to see it in an example. The first correction to the energy of the black hole basically goes like temperature squared, okay? And then there's further corrections here. This, you can just do it from knowing the laws of black hole mechanics. You can basically see how the mass of the black hole basically behaves as a function of temperature, okay? So the available thermal energy, just to be explicit, like how much energy do I have if I turn on the temperature, is basically something that goes like T squared divided by this n gap here, this parameter. I'll tell you in a moment why I'm calling it n gap. So this is something that will depend on the extremal parameters of the black hole. Okay? So that's about available thermodynamic energy. Now, on the other side, the counterpart, you can say, well, you turned on a little bit the temperature, right? So if you turn on a little bit the temperature, you should be able to emit a Hawking quantum, okay? And so the Hawking radiation will basically emit quanta, will emit radiation with energy, let me call it a delta E H. So let me maybe call this one to be emphatic, the thermal, the thermodynamic energy accessible. If you look at the Hawking quanta, so a single quanta basically will be h times nu, since the frequency of this quanta. And this is basically something that is going to be linear with the temperature of the black hole. Because I'm basically taking here that the wavelength of one of these quanta goes like 1 over the temperature of the black hole. So intuitively, just from dimensional analysis, you would say, okay, a single Hawking quantum basically will require energy that is linear with the temperature. Okay? And now the puzzle comes. comparing t squared versus t. So if I plot simply the energy of the black hole against the temperature, this EH will basically be a linear function of temperature. Maybe I should have put it against 0, but it doesn't matter. And so this is how much energy I need to emit one Hawking quantum. But something that is quadratic at low temperatures basically will go below it, that line, that straight line. And so there's a whole range of temperatures for which the parabola, the thermodynamic energy, maybe I should have drawn it. Let me draw it with yellow. Where this thermodynamic energy is much less than the Hawking quantum that I need. So in this range, I can't even emit a Hawking quantum. And that's problematic. Because I started turning on the temperature and I can't even do that process of thermal radiation. Okay? And so the problem is that, so let me mark the point where they intersect. So this is usually called the temperature breakdown. And here the intersection, you can see that when you equate this quadratic answer to that temperature answer, to that linear response there, this is where you get m gap. Okay, so the parabola is equal to the linear part, and when t is basically of the order of m gap as well. So basically, the semi-classical energy of the black hole is less than the average energy of radiation below this m gap. And this also presented a problem. Why is this happening? And the answer that was given at the time, an unsatisfactory answer, was to say, well, maybe there's a gap in the spectrum. That's also why it was called M gap. Maybe the spectrum of the black hole, if you consider what are the allowed energy eigenstates, maybe there's no states available up to this energy. So if you have a gap in the spectrum, and this is your first, so you have the ground state, and then your first excited state comes here, then you don't have a puzzle. Because then you need to reach that energy, that first allowed state in the spectrum, to kind of go and be able to emit your first Hawking quantum. Okay? So here in this range, you wouldn't be able to emit a Hawking quantum, but then you would have to have a gap. But there was no explanation for that gap. Like, I don't know what the spectrum of the black hole is. This is all part of the agenda. But generically, there seems to be a problem. So if we trust this formula, and we trust our entropy, then in order to make sense of this picture, it must be that the spectrum of the black hole has a gap. Okay? So the only explanation, old, spectrum. Okay, so basically just schematically, it would mean that if I plot the density of states as a function of energy, I would have had a lot of ground state degeneracy at some point, and then at some E gap, then there's a gap in the spectrum, there's no states, and then you start having some density of states after some value. Okay, ideally discrete, but I'm just drawing it like this. It doesn't have to be necessarily this shape or anything like this, but the important part is that you would have thought there was a little gap there. And so you are not allowed to emit, there's nothing for you to emit in this range, and so then you don't have this issue of the parabola going underneath the straight line. Okay? But again, why would that, like, okay, if you have a theory of quantum gravity, basically, so what I'm basically saying with these two puzzles here is that if you have a proposed theory of quantum gravity, your theory of quantum gravity should address these two puzzles, right? There should be a prediction that there should be a huge amount of entropy, and that there should have been a gap in the spectrum such that this effect is compatible. Okay? Now, what I'm going to tell you, what these lectures are going to be about, is basically going to be about, well, the goal of what I hope to get to by the end of Friday. Wait. Yeah, this is annoying, right? Because now I pull this down. Did you guys write this down? Or should I erase the block? No, I'll just erase it. So, the goal, basically, of these lectures is going to be to address these two issues. So these two problems that we have. And the way that we're going to do that, the way that we're going to address these issues, and I'm going to explain to you how you should understand them, is that we're going to use the gravitational path entropy. So we're going to revisit these questions, okay, with this as a tool. And the lesson, which is actually more important than the goal, so we were talking about today during lunch, this is about learning tools. It's not going to be about the specific question we had in mind. But the lesson that you will learn from this is that by trying to address this, you're going to realize that classical aspects, classical results, or semi-classical, can change drastically due to quantum effects. Okay? So everything that I actually have presented to you so far and summarized and given you some motivation, it's based on semi-classical analysis, semi-classical results, and trusting that that was the biggest and most dominant effect. And this is a situation, which is a beautiful situation in quantum gravity, where we're going to see that quantum effects are actually more important. Okay? And we're going to learn that, we're going to see that by looking at this gravitational path. Okay? It's one of the results that it could have been done in the 70s. It wasn't, but it's just so beautiful as a result and as an outcome. Okay? And it's something where you have to understand how to go against the dogma. Okay? How to go against what you were taught what I teach when I teach path integrals. How do you think about perturbation theory? How do you think about what are the most important effects? Okay? So this is what I want you to keep in mind as a task. Look for cases where the classical results are not actually the most dominant.
I was personally asking that there is an example in quantum field theory that we know that this is true.
Yeah, it's not the only, an example in quantum, well, in the similar fashion as what I'm saying now, yes and no. Yes, because everything that I do in gravity has a dual in ADS-CFT. So yes, I know what is this, the version of this effect, of this same effect in conformal field theory, let's say. So I can tell you precisely what is this. But it's not just, there are other situations in quantum field theory where, yeah, you can have like non-perturbative effects, or you can have like effects by instance on your solitons that tell you, that maybe give you something that is counterintuitive. Or effects of resurgence, for instance, where a whole infinite series of perturbative corrections like resum to give you a non-perturbative effect. So there are situations. They're not usual. They're not typical. So, but this is where the fun part of physics comes in, discovering something new from doing this. Now, the difference here is that I'm not going to tell you like, oh, there's a big non-perturbative effect coming in. That's not going to be the punchline. It is going to be perturbative quantum gravity that will tell you that the first quantum corrections were actually more important than the classical correction. That I haven't seen, again, because of ADS-CFT, I've seen it in the CFT, but I haven't seen it in other situations. But that just might be my ignorance. Okay? So very good. So this is basically what I want to do. Okay? And so to do that, the outline, how we're going to structure these lectures. So now I will move it down. So the outline for these lectures is that I'm first going to tell you now what I have, the time that I have left. We'll talk about the gravitational path integral. And we're just going to, so I'll start with this, just some general statements. We'll talk about the action. We'll decide on what action we want to use. Look at a black hole in this theory, which I'm going to pick, again, just because it's going to be simple. I'm going to look at the Near-Extremal black hole, and then I'll tell you a little bit about the thermodynamics, black hole thermo, from the gravitational path integral. So this goes back to these results of the 70s of Gibbons and Hawking, and so we're going to just review that part to start. Okay. Then the second part of these lectures. What I want to do then is to start looking at the quantum corrections. But I'm going to start basically on looking at one loop effects on extremal black holes. So this is basically, I am going to show you here some very interesting things that happen on extremal black holes, but it's mostly going to be a technical exposition of like how do you deal with these quantum corrections. Okay, so what are the tools that I'll need to compute them, to capture them, just setting up basically the notation and the computations. Okay, and then in the third lecture by Friday, we'll do again quantum corrections. But then we're going to do them near-extremal. So, which should be simple to do once, well, they're still quite complicated computations, but they're going to be much simpler once we know what is this quantity that we're going to compute. Okay? So this is roughly the structure of the lectures. Very good. Are we ready to start? It was just the warm-up, the hand waving part. Okay. Very good. So let's just set up the gravitational path.
Ale?
Yeah.
Will you be working with the gravitational action, the normal times and
Yes.
So then, we know that this is not normalized, so what will be the interpretation?
It will be the interpretation. Very good. So this is something I was too lazy to write it down. I'm happy that you said it. I don't need it to be renormalizable. I'm not afraid of non-renormalizable theories. It's fine. There's an infinite series of counter terms, but I don't need to know the entire series.
The higher order term can be another order.
Oh, but that's what, it will be part of what I'm going to justify here, because I don't need to know all the quantum corrections. I just need to be able to extract some of the important ones. And that's already going to illustrate that there's a bigger effect that is overshadowing the classical effect. So I'm going to take a point of view of low energy effective field theory. So GR as a low energy effective field theory is perfectly well defined, and I can always treat it perturbatively. There's still going to be, let me tell you about the assumptions as well as I'll do, but I'm basically going to take that mindset. Okay, so I have a low energy theory, there's going to be a tree level contribution, there will be a one loop contribution. What does it look like to do those computations? And yes, there will be divergences. Yes, you do have to add counter terms. There's a whole series of them. But it's still something that order by order, you can compute. It takes a lot, it won't end, but order by order, you can renormalize the theory and find appropriate counter terms. But the beautiful thing that I'll show you is that, yeah, so this is also why people sometimes they venture into this, because they say, what's the point of doing a quantum correction if the theory is not renormalizable? But still, there's information there. There's still information in the low energy theory that is interesting, and that will guide you in understanding what quantum gravity might mean. Because even if you know what quantum gravity is, if you have a unique completion, and you say, this is whatever string theory, whatever it is that you want to understand, that UV theory then still needs to reproduce the low energy predictions. And these low energy predictions that I'll show are robust. They do not depend on basically how you're renormalizing the theory. So I'm going to be focusing on quantum corrections that don't depend on how I'm renormalizing the theory. Yeah. Of course, there are corrections that should depend on it. So if you have higher derivative terms and stuff, they will depend on it. But the quantum corrections that I'll show to you do not depend on the renormalization scheme, or at least as far as I can tell. If they do, if you do see that they depend, then we should definitely write to the authors and tell them that maybe the conclusions are wrong for that reason. But yeah. Okay. Very good. So the main object that we'll have in mind will be the scary object. It's one of the least well-defined objects in life. But basically, I'm going to be considering this a gravitational path integral, where I'll be integrating over all possible metrics, all possible fields. So I'll also couple matter here to this, of a Euclidean action that couples gravity to those matter fields. Okay? So this will be, as I'm already indicating here, I'm going to be doing a Euclidean computation of this gravitational pattern. Okay? And there's always, of course, boundary conditions that you have to provide for the fields and for the metric. and we will have those such specifications, but this is basically the object, okay? So this object here goes back to the 70s. And Hawking. And of course, like, in a sense, we write these symbols. And I'm not going to tell you that you fully understand what are the rules of computing this. This is not what I'm going to say. But there's basically, like, so what these gentlemen did, they gave possible rules, to evaluate this PPI. And at that time, what they showed with their rules is that you could reproduce, for instance, everything that you knew with these rules. You could reproduce, for instance, black hole thermodynamics. Okay, so this at that time was kind of nice. Okay, so you wanted to reproduce black hole thermodynamics. You can use this gravitational, this Euclidean path integral. It was all good to go. Okay. And so what we're going to do now is use those same plausible rules. So what are our assumptions? So now, let me write it today. So what happens since the 70s? Let me put here, reproduce black hole from. Okay, so what are these rules? So the rules that basically they proposed was to say, look, and it's an important assumption, something that is not clear, but there's a few things that go into this, but basically what they proposed was to say, look, think of this gravitational path integral as a saddle point approximation. So what does it mean to think of it as a saddle point approximation? They said, look, maybe this path integral, this gravitational path integral, I can't do these quantum integrals, but perhaps you can approximate it by a sum over classical solutions. So let's say you look at what the equations of motions for this gravitational action is. So you will have some classical solutions, and the path integral should be weighted by the on-shell value. So when I write down I, it means that it's the on-shell value of the action. This is just convention, just not to confuse them. So it's basically going to be weighted by the on-shell action on the solution, and then plus corrections. So these are the quantum corrections. Okay. This part here, this is what I'm calling this. This is what I will call the tree level action. And then here you can have higher corrections, higher derivative corrections to this action. Okay? So this is how I'm going to understand this gravitational path integral. Now we will want to do it around a black hole, and so there will be further the approximation that here I'm going to take the most. So let me write this again. Let me write it as some C for a given solution. And here we're going to consider that the black hole is the solution that we'll be at least focusing on. It might not be, again, there's some asterisks here, but basically we're going to take the black hole to be the most dominant contribution, okay? Or at least the contribution that we'll focus on, okay? So I'll look at what this path integral here is around this black hole solution. Okay? So this is how we're going to think about this problem. Yes?
If there is no classification for manifolds, how do you know?
No, I don't.
Classify this sum?
I don't.
So,
I don't. So that's why, okay, so there's various things, so that's why you're kind of like, this could have been an objection to absolutely everything one does. So, yeah, this is the problem of making a definition of this, or actually trying to understand carefully what are these rules, right? So for instance, something that is implicit here, as we define these classical solutions, I should also have said classical solutions that are smooth. Should I have singular solutions? Still. Even if I say regular. Even if I say regular, you might have problems. It could also be that there are off-shell solutions that contribute. It doesn't have to be that the saddle points. So these are the saddle points. There's nothing tells me actually why the saddle points have to be classical solutions. It could be that the saddle points are off-shell configurations. And there's actually nowadays situations related to these wormhole solutions where people are considering off-shell solutions as contributions to the gravitational path integral. So I have absolutely no clue. Now, there are certain theories of gravity in low dimensions, so for instance in 2 dimensions and in 3 dimensions. In certain situations I can classify all regular manifolds. And there, even in those situations, people have attempted to do the sum. And there's still some interesting puzzles. In terms of what does this mean as a microscopic system. But we're going to just take the attitude, again, I don't need to compute this path integral exactly. So that's going to be part of my point.
it's totally fine, but how can I know that this is the dominant contribution?
No, I don't. I don't. It's basically part of the question would be do you think that so what this computation, what this tree level computation tells me, it reproduces the entropy of the black hole, basically. So that's why I'm going to focus on the contribution around the black hole, because I want to say something about the statistical nature of the black hole. So I'm going to take this as basically, if you want, as the mini partition function for the black hole, and try to see if I can say something about these issues that I was finding with the entropy and with the energy of the system. What can I say about that huge amount of degeneracy and about the energy that the black hole had accessible from looking at this object? So I'm trying to isolate the black hole in some sense. But I agree, I don't know how to do this. I don't know how to do all the sums, but it's not going to be But these are all good questions, because what I'm going to, and it's one of the important questions in quantum gravity, what does it mean to do this computation and get it compatible with a UV complete, discrete quantum system. Okay.
My plan for the lecture tomorrow is precisely compute that classical contribution, so I hope you'll remember to say
No,
that.
I was just going to write the answer. Oh, then that's great. That's amazing.
And your topic is right after mine, so we're synchronized.
Oh, okay.
I'll do that calculation and then you do the other one.
Yes. Okay. I think because I still have time, I was just going to write the answers. But yeah, I was not actually, because then I will not have enough time. Oh, this is amazing. Okay, we did not carve it then. This is really cool. No, because there's a lot. I was just going to throw it under the rug and be apologizing all the time, I'm sorry, I can't show you how this is done. But then Max will teach you how to do that. Oh, that's great. Okay. Okay. So this is what I want to have you guys in mind. Okay. So we're going to be doing this gravitational path integral around a black hole solution, and this is the main object. Okay. But now let's pick an action. I don't know if we're going to use the same action. Probably we'll pick, but look, even if we pick a different theory, the method is always very, like the philosophy is always similar. So don't like, it's okay if or maybe we might have it to be. Yes.
Question. The partition function are not the propagators of GravUC.
What's that?
But for gravity, in sense, I need to understand what is the meaning of the partition function, the gravitational integrals.
What is the meaning of this?
Yes.
Like in life.
No.
If you want, view it like the sorry.
I try to understand I this in Spanish. So
Yeah, no, go ahead.
estoy tratando de entender que esto es la interacción de la materia con la parte gravitacional.
Sí. Yes.
¿No?
Let me write an action and just to demystify what I'm saying. So I'm basically going to so the action that we're going to be using for most of it, just in terms of the black hole. So this Euclidean action. I'm going to have in mind that is the Einstein-Hilbert term in 4 dimensions minus f squared. Okay, so Einstein-Maxwell. So here I have gravity coupled to matter. It's one example. So this is the metric part, and my phi I is the gauge field in F. And so this is a theory that couples gravity to matter. It's one example, but just to show you a black hole in it, what would be the entropy of it, and stuff. But we don't like this action.
Cuando uno dice que uno está sumando sobre las métricas,
Sí.
también está considerando métricas que no satisfacen las ecuaciones de opción. ¿No?
In principle, like, okay, so again, for what I'm going to say, okay, so there's two things here. So usually, just to clarify the notation, when people say that there's a saddle point approximation for the path integral, well, again, it might depend on the person. I'm just saying, like, we're going to take basically as perhaps a good approximation for the path integral, that the most dominant contributions come from the classical solutions. It's an assumption. I'm not proving this. So it's part of my plausible rules. And then what I'm going to do, so around each of those classical solutions, there's going to be quantum effects. So that's what this object basically is encoding. So those quantum effects, they're not necessarily on shell. You're looking at fluctuations basically around each of those classical solutions.
Las fluctuaciones pueden ser opción.
See? Yes. And there will be for us, because we'll be doing a one-loop determinant. And those are, you basically integrate overall possible considerations. Yeah. So we'll be doing something fun. Of course, if you just focus on the tree level part, the first contribution that you get is just on shell. Right? So this is the tree level part, but then if you start doing loop corrections, you have to do your quantum physics. So if you want, like in terms of diagrams, you will have like, that's the tree level diagram, and then you will have little graviton spin exchange. So that's your one loop, and off you go. So what I mean by those little dots is basically keep on adding loops to your diagrams. Okay?
Sorry?
Or,
No, you go.
Rose.
In your comment about wormholes,
Yeah.
you said that those lines compute like off-shell configurations as solid points.
Well, they look at the, Yeah, so it's a long story, but basically, in order to reproduce a two-sided wormhole path integral, they have to look at a solution that is an off-shell solution to Eisenberg. So these are the results of Jensen and Cutler-Jensen. So those are not solutions to the Eisenberg equations. Or if you want, they're solutions with a delta function in them. But in order to get this spectral form factor that it's characteristic of these two-sided wormholes, the only way that people know how to reproduce that spectral form factor is by looking to off-shell configurations. Because there's actually no on-shell solution. Yeah, that's the result that I was referring to. And then in JT gravity, there's also versions of this happening as well. So you
Because we have the usual standard that some point are kind of on-shell because they are
Yeah, exactly. So the reason why this was a good assumption is because classical solutions externalize the action, and you're looking for basically the maximum contribution. And so that's why it's an okay assumption. So if you're off-shell, you would have thought, oh, the contribution, maybe they are there, but then I would have added them as like, they're exponentially suppressed, and then I don't care that much about them in the limit as G Newton is going to 0. But so the reason why, you tend to be able to approximate path integrals in this way is because, the on-shell solutions, by definition, externalize the action near the biggest contribution. And so you look for that solution. So you know that they're going to give you, they're going to give you a big contribution to the path integral. It's not going to be the only one, but you know that it's going to be a very dominant contribution. Yes.
Excuse me, the coupling of Maxwell to the curvature is done only through the determinant of the spacetime, or do you need to covariantize the already covariant? But the derivatives that are inside of F mu are okay, yeah, great.
Just to make it explicit.
Yeah.
And this guy, it doesn't matter if I write partially or very derivatives. Okay? Any other questions? I know writing path integrals, gravitational path integrals, is extremely controversial. Bear with me. There's a lot to learn from doing a gravitational path integral, even if you're making this assumption. But of course, the challenge for you guys, what I'm going to be doing, presenting to you here, is like the easy computation. What you guys have to do is then all of these questions that you've been asking me, like being like, okay, let's go further, let's go farther. Can we apply it to other situations? So, yeah. Okay.
Sorry?
Yes.
I have a question with mass gap concept.
Yeah. Let's see. Is it still behind here?
When you write the fact that there's a significant expansion of the energy of the black hole, the mass gap, it doesn't mean that it's equal to 0. The gap, or if it's not well defined.
Oh, if this is not well defined? No, well,
That's the meaning of the gap.
Oh, the meaning of the, so this is a number, well, I'm about to write it for an explicit black hole.
That can lead to a divergence in separation function.
No, but this, okay, let me, so when you do a semi-classical analysis of like the mass of the black hole, these are just going to depend on parameters of the black hole. It's just going to be something that, maybe let me write it down, and then it will be less dismissive. I called it, so whatever number, whatever constants I get here, I just kind of gave them a name, and I called it M gap, because it is the point where you should have a gap in the spectrum to resolve this puzzle. So it's just nomenclature for now. Okay, so it's just basically when t squared is equal to t. So when is t squared equal to t is when t is basically m. That's
But that T is not the
it's a Hawking temperature. It is the Hawking temperature. Yeah. Okay, let's write down. I know. Let's do this for Russian nostril.
That's
Let's do it the Russian nostril. So then I know. So let's do this. Okay. Oh, and maybe you'll write the boundary term. Max, are we using the same action?
Sorry, say that again?
Are you using the same action?
Without the S.
Okay.
So I can do that. If you want me to do it,
No, it's fine. I was just going to write down, so this is the action, and also because we were concerned about having a good extremisation principle, I was going to write down the boundary terms. So, there's also boundary terms here. So Max will write down the Gibbons-Hawking term, the extrinsic curvature, but then there's also, if you have a field strength, you also need that term as a boundary term to fix the gauge.
actually, I will claim that boundary term is not good.
This one?
No, the first one.
Okay. I know that it's in general, like in life, like even for Dirichlet boundary conditions.
Well, it depends on your boundary conditions.
Oh, of course, I have Dirichlet boundary conditions. Are we okay? No.
Well,
Yeah, no, of course. The boundary terms that I'm writing depends on which boundary conditions I have, but just, yeah, we'll be working with Dirichlet boundary conditions. But okay, let's write down, or maybe let me erase this, but let me not erase that so that equation can still be seen.
the thing is, it is divergent. You still have to.
Yeah, there's still a counter terms. Yeah, but okay, you'll do it. Yeah, there's still a boundary counter term, and well, yeah. So this is also why I didn't want it to go into the whole thing, because yeah, you still have a divergence, and yeah, you either have to add a counter term or do this minimal subtraction. Like, yeah, Max will tell you all about it. It's a beautiful computation, though. It's super useful. I'll be very curious how he presents it. But okay. So we have the action there. Now let's look at the Weissenostrom black hole, which is going to be a solution in this case. And so I'll write it in Euclidean signature. So this is the Weissenostrom solution. This is going to be our G0BH and A0BH. And then basically the Weissenostrom solution is characterized by two horizons, which are the zeros of this function f of r, which defines r plus and r minus. As m squared minus q squared. Okay? And here m and q are constants. They're basically in appropriate units are the mass and Q, the charge of the black hole, and there's the gauge field that supports it. I wrote it in Euclidean signatures, and you can see here where there's a plus in the dt squared, and that's why there's an I there sitting in front of the gauge field. Okay? If you're bothered by that, write it in Lorentzian signature. But that's the Euclidean solution. Okay? So now let's write some properties of this black hole. So what's going to be useful?
Alejandra, why do you fix the potential to 0 at the horizon? What do you need it?
It facilitates the computation. It's regularity at the horizon. That's why you fix it to 0.
You have to.
Yeah. When you do basically the computations that Max wants to do to compute the on-shell action, you need to have the gauge field equal to 0 at the horizon. The regularity of like the Euclidean cigar. Cinco? Cinco. Okay. Yeah. Okay. Because remember, in Euclidean signature, time is periodic. So you want the gauge field to not have like a lot of around that point. Okay. So what we're going to do then, okay, so in this language here, for instance, the Hawking temperature is defined I'm going to write it in this way. A little bit different. The mass, let me rewrite the mass. So we're going to do something funny. And I'm going to write everything, so what, sorry, there's a square here. Usually people write it as a function of R plus and R minus. But I'm writing everything in terms of R plus and Q. Okay? Just because I'm going to fix it in a way, and then R minus is Q squared over R plus. And then if you compute the on-shell action, this I0.
Sorry? How do you define M? 1 over
2 times R plus. So and Max will tell you how you get this.
Only case with electron charge, just to the lines.
Here beta is 1 over t. And then from this on-shell action, so this is just to illustrate the results of Gibbons and Hawking. So for instance, the energy of the system is basically the derivative of I with respect to beta. You can check that if you take a derivative with respect to beta of this thing, you basically reproduce this expression here. Oh, here I should say, sorry, there's a 1 over 16 pi to Newton. We put it in there. And then if you wanted to compute the entropy, let me write it down here. So I have 2 minutes left. The entropy in this formulation is basically beta E minus I0. And what you will find is that it's pi R plus squared over G. Okay? So these are the basic thermodynamic properties of this Weissenhoff black hole. Okay? Now, this is for the generic black hole at any given M and Q. If you go to extremality, well, let's erase this part. So now extremal Rn is basically equal to Q equal to something that I'm going to call R naught, and this R naught, you can also see it from here. What I'm calling R naught is basically the fact that R plus is equal to R minus, okay? And as advertised, when M is equal to Q and equal to R plus, you can see from here, for instance, that the temperature goes to 0. So it will be this T equal to 0 limit. And maybe, no, 3:30. Okay, now I'm going to rush to my story. So what I'm going to do tomorrow, sorry for that. We're going to start here again, just so that I actually finish on time the first time around. So we'll talk about this extremal black hole, the near-extremal limit, and then clarify some of the questions being asked about this. So let's stop here, and then continue.